This video will be covering ammonia. So let's start. The laboratory preparation reaction starts with NH4Cl ammonium chloride plus calcium hydroxide in the presence of heat. The reactants are heated to produce calcium chloride, water and ammonia. Ammonia is the material or the substance that is needed. And let's look at the conditions and the reasons for the laboratory preparation of ammonia. So calcium hydroxide is used since it is cheap and not deliquescent. So deliquescent means that a substance which absorbs as much moisture as there is in the air, and calcium hydroxide is not deliquescent unlike other caustic alkalis. Then we have NH4NO3, which is also ammonium nitrate, and it is not used since it is explosive in nature and may decompose. Due to its explosive property, it is used in explosives such as TNT. Then let's scroll down a bit. Round bottom flask is kept in an inclined position. So that water vapor formed may not trickle back and crack the hot flask. Reactants are ground thoroughly and to provide maximum surface area for reaction. So if you have a huge block of say for example iron, so ground thoroughly means you divide this into very small pieces of this whole iron block so that it provides maximum surface area for reaction. Quicklime drying agent, its chemical formula is CaO, calcium oxide. Agent is used since it is basic in nature and it does not react with basic ammonia gas. So unlike the other drying agents such as H2SO4, P2O5 and fused CaCl2, all of them are acidic and they are acids or salts which react with ammonia, and you do not want that to happen. You want a non-reactive drying agent which does not interfere in the reaction. So quicklime drying agent is used, and then we have ammonia, which is collected by downward displacement of air since it is lighter than air. And then we finally have ammonia gas is not collected over water since it is highly soluble in water. So that these are some properties that you have to remember. It is lighter than air and it is highly soluble in water, and they may ask you in exam the mode of collection of ammonia. So you have to write it is collected by downward displacement of air since it is lighter than air. You have to also mention the reason. Okay, let's move on to the Haber's process, the manufacture of ammonia. Okay, so let's move on. N2 plus 3H2, and this is a reversible reaction, gives 2NH3, which is ammonia, and if you see a triangle like this at the end of the reaction, then it means that the reaction is exothermic. These are some properties of the reaction. It is reversible, it is exothermic, and low temperature and high pressure favor the forward reaction, because you want as much yield of ammonia as possible. Now we have some properties of the reaction. Temperature is 450 to 500 degrees Celsius. Please do remember the range. And then we have pressure, which is 200 to 900 atmosphere. Catalyst is finely divided iron. Finely divided in the sense, as I said before, if you have a huge block of iron, so you don't dip the whole block of iron in the reaction itself. You ground this whole block thoroughly into smaller pieces so that maximum surface area is provided for reaction. And then we have promoter, which is molybdenum, and impurities such as carbon monoxide, carbon dioxide and hydrogen sulfide. Now there are some reasons associated with this. Nitrogen gas is obtained from fractional distillation of liquid air because air contains nitrogen. Hydrogen is obtained from water gas, Bosch process. We move on to the next condition for the manufacture of nitric acid. Increase in concentration of the reactants favors the forward reaction so that there is maximum yield of ammonia. Reactants should be free from impurities. This is a very important question that is asked in boards every year, since they tend to poison the catalyst. This is point number 1, and hence reduce its effectiveness. This is point number 2. So these 2 points have to be mentioned in the answer to the question, why should reactants be free from impurities? Question mark. And this is the answer. If the temperature is too low, the speed of the reaction will be slow and hence the yield of ammonia will be low. So that's why you need a balance. The balance is also called an optimum temperature, which is 450 to 500 degrees Celsius. And there is one more reason given over here, but above the optimum temperature, if you take the temperature also too high, ammonia may decompose to form nitrogen and hydrogen. Okay, let's move on to the next question. External heating is not required after the reactants are initially heated, since the reaction is exothermic. So this is the reason. Since the reaction is exothermic, that is, the evolved heat further maintains the reaction's temperature. So this is a very important question that they may ask. Why is external heating not required after the reactants are initially heated? Question mark. And this is the answer. If pressure is too high, the production plant may not withstand the pressure. So the more the pressure, the better. But if you take the pressure too high, the production plant may not withstand the pressure. And in order to withstand the pressure, you have to build thicker walls, and it would add to your maintenance cost. You do not want that. So hence optimum temperature 200 to 900 atmosphere is used. This is the optimum temperature, optimum pressure. The catalyst, that is finely divided iron, is mixed with small amounts of promoter, that is molybdenum, which enhances the efficiency of the catalyst. So this is a major function of a promoter. Okay, let's move on. These techniques are used for separating ammonia from the uncombined nitrogen and hydrogen. So in the reaction, you have NH3 and you have traces of N2 and H2. So you have to separate these from ammonia. For that, there are two ways. One is liquefaction. Now in liquefaction, ammonia is easily liquefiable, condenses to liquid around minus 33 degrees Celsius. So it is very easily converted to liquid. But if you take N2 and H2, that is nitrogen and hydrogen, they are very, very difficult to liquefy because they have very, very low temperatures wherein they could convert to liquid around minus 196 degrees Celsius and minus 253 degrees Celsius respectively. Now let's move on to the next method for separating unreacted N2 and H2 from ammonia. So this is dissolving in water. Ammonia is highly soluble in water, N2 and H2 are almost insoluble in water. So this is the way in which you could separate ammonia from uncombined nitrogen and hydrogen. Now physical properties of ammonia, it is colorless, it has a strong pungent smell, it has a slightly alkaline taste. Okay. It is lighter than air and it is highly soluble in water. This is a very important property, lighter than air, highly soluble in water, and this is the reason for the collection of ammonia in the laboratory preparation that we studied earlier. Chemical properties of ammonia are, so these were the physical properties, and the chemical properties are neither combustible nor a supporter of combustion, and the section that we will study henceforth will be the chemical properties of ammonia. Now we will study the burning of oxygen. Now in the burning of oxygen, ammonia is burnt in excess of oxygen to produce nitrogen and water. So this is a rough representation of the entire reaction. So this is a greenish yellow flame, this is a greenish yellow flame, this is a cotton, and these are ignition tubes. Okay, dry ammonia gas passed through ignition tube A and ignited alone does not burn. So you need something with which dry ammonia gas can be burnt. Now let's study what that substance is. After passage of oxygen, ammonia burns in an atmosphere of excess oxygen, special emphasis on excess, with a green or greenish yellow flame forming nitrogen and water. So these are the two products formed when you burn ammonia and oxygen. Now let's move on to the catalytic oxidation of ammonia. So whenever you hear the word catalytic, you know that in the reaction there is a use of catalyst. Now in this case, the use of catalyst is platinum. This is ammonia, this is oxygen. They are combined in with the help of catalyst platinum at around temperatures of 800 degrees Celsius, and it produces, this is known as nitrogen monoxide plus 6H2O plus triangle. Now triangle means heat, and thereby the reaction is exothermic. Now this is not exactly water, this is steam. Okay, now let's look at the figure. So you have dry oxygen and dry nitrogen going inside this tube which contains platinum, catalyst, there's a reaction, and then finally right over here, so nitric oxide is produced, and colorless nitric oxide. So please note the colors of these substances. colorless nitric oxide is formed which on oxidation, oxidation means addition of oxygen, gives reddish brown nitrogen dioxide. So first nitric oxide's color was colorless, but now nitrogen dioxide or NO2, its color is reddish brown. So you would see a reddish brown gas which would be formed in the flask. Okay, and this is the reaction. Nitric oxide plus oxygen gives nitrogen dioxide. The platinum catalyst, so platinum is the catalyst, continues to glow even after heating, is discontinued since the catalytic oxidation of ammonia is an exothermic reaction and the evolved heat further maintains the temperature of the reaction. Okay, so let's move on to the next document. Now let's study liquor ammonia. Now liquor ammonia is basically part of the section of chemical properties of ammonia and it represents ammonia gas's basic nature. So let me write that down. This represents ammonia gas basic nature. An aqueous solution of ammonia gas. Now special emphasis on gas, it could either be ammonia gas or acid. In this case it is gas. An aqueous solution of ammonia gas in water is called liquor ammonia or liquor ammonia fortis. It is prepared by dissolving ammonia gas into water using a funnel arrangement similar to the preparation of HCl acid from HCl gas. So this is the reaction that is mentioned. NH3 plus H2O gives NH4OH, which is also known as liquor ammonia or ammonium hydroxide. Now let's move on. Perfectly dry ammonia gas is neutral to dry litmus, but aqueous solution of ammonia turns red litmus blue and phenolphthalein solution pink. So this is solution. Now let's move on. Now please note that ammonium hydroxide is also known as the aqueous form of ammonia. And now we will be studying the reactions wherein ammonia is reacted with different kinds of acid to produce different kinds of products. But as you may know, water is formed in all three of them. So you reacting aqueous form of ammonia with different acids such as HCl, HNO3 and H2SO4, and each one of these are dilute. So NH4OH or ammonium hydroxide reacts with HCl to form ammonium chloride and water. Ammonium hydroxide reacts with HNO3 to produce NH4NO3 or ammonium nitrate plus water, and then finally NH4OH plus this is the balanced form, this is the balanced reaction. NH4OH plus H2SO4, dilute H2SO4 or sulfuric acid gives ammonium sulfate plus water. Okay, so let's move on. Now we will study the precipitate reactions, wherein the ammonium hydroxide or the aqueous form of ammonia will be reacted with various kinds of metallic sulfates, chlorides, nitrates, sulfates, etc.
Color change is important.
And color change is also important. Color change is very important. Now FeSO4 plus 2NH4OH, let me change the color first, gives NH4 2SO4 ammonium sulfate plus FeOH twice. Now in each of the following reactions, the product will be a precipitate, that is it is insoluble in the solution. Now iron hydroxide is dirty green. Ferric chloride plus NH4OH, aqueous form of ammonia, gives ammonium chloride plus iron 3 hydroxide, and it is reddish brown. The precipitate is reddish brown. Okay. PbNO3 twice or lead nitrate plus NH4OH gives NH4. It gives NH4NO3 ammonium nitrate plus lead hydroxide. It is a precipitate and its color is chalky white. And then we move on to ZnSO4, zinc sulfate plus ammonium hydroxide gives ammonium sulfate plus zinc hydroxide, which is also precipitate, and it is white gelatinous. Copper sulfate plus ammonium hydroxide gives ammonium sulfate plus copper hydroxide, which is pale blue in color. Okay. Now let's move on to the next reaction. Copper hydroxide plus ammonium sulfate plus ammonium hydroxide in excess produces tetramine copper sulfate plus water, and the color of tetramine copper sulfate is deep blue or inky blue solution. So either of these two. Okay, so let's move on. Now reducing heated metallic oxides to metals. You have copper oxide which is a metallic oxide, and we have one more metallic oxide, which is lead oxide. Now let's look at the color of each of these metallic oxides. It is black, copper oxide is black, and lead oxide has the color buff yellow. So reducing heated metallic oxides to metals, and copper oxide, the metallic oxide, is reduced to copper, and lead oxide is reduced to its respective metal, which is lead. So in this reaction, black copper oxide is reduced to brown copper as visible above. And let's move on to the second reaction. Lead oxide is converted to 3Pb, which is lead form. Buff yellow lead oxide, this is the color is very important, is reduced to grayish metallic lead. So this was the reducing heated metallic oxides to So this section is basically when ammonia reduces chlorine to hydrogen chloride. So in this case, ammonia is in excess, which is added to chlorine, which forms NH4Cl, ammonium chloride, plus nitrogen, which is a gas, which is liberated as a gas, and dense white fumes are seen when ammonia reacts with both HCl and Cl2. And then moving on to the next reaction, in this case we have chlorine, which is in excess. So first we had ammonia, which was in excess, now we have chlorine, which is passed in excess, and the products are very different from what it was before. In this case, hydrogen chloride is formed and nitrogen trichloride is formed. So remember the colors. Colorless ammonia gas reacts with greenish yellow excess chlorine, giving a yellow explosive liquid, also known as nitrogen chloride, trichloride, or NCl3. Now action on indicators, so it turns moist litmus, I forgot to add over here, moist litmus red to blue, and it turns methyl orange from orange to yellow, phenolphthalein from colorless to pink. Now let's look at the uses of ammonia. So it is a source of hydrogen as well as nitric acid, Oswald's process. It is also used in manufacture of explosives, ammonium nitrate, baking soda. Remember the formulas of these compounds. So you have NaHCO3. In exam they may ask you baking soda, so you have to write the formula. You cannot write, if they give you say for example chemical formula like NaHCO3, you could write sodium bicarbonate as given over here, but mostly it is known as baking soda. And then you have washing soda, whose chemical abbreviation is Na2CO3.10H2O. It is also used in fertilizers. This is the formula: urea, ammonium sulfate, ammonium nitrate. The formulas are mentioned over here. And then we move on to ammonium compounds. So ammonium carbonate is used in smelling salt, revives a fainted person, and it is used in baking and dyeing industry. Now what about ammonium chloride? It is used in cleaning metal surfaces and used in dry cells, medicines, and textile industry. And finally, what about ammonium sulfate? It is an important fertilizer and used in manufacturing of alum. Now let's move on. Liquor ammonia. Now what is liquor ammonia used for? It is used for it emulsifies fats and grease stains, hence used in removing oil and grease stains from clothes. It is also used for cleaning window panes, porcelain articles, etc. So that brings us to the end of this video. I hope you learnt and enjoyed this video. This video will be uploaded to IsEqualTo Klasses Shivang, so be sure to check the video out there. Stay home, stay safe, take care, and I'll see you in the next video. Thank you.